Welcome back to geometry. This time actually pause the tape and find the volume of these solids before we move on. For our first solid, we're going to have the area of a triangle, which is 1/2 base times height of the triangle times the height of the shape. So that's going to end up being 24 times 7, which is 168. And please never forget the units at the end. I don't tend to write them while I'm doing this part because it messes it up. But remember your units. Doesn't matter which one you consider base here. It can be 4 times 10 times 12, which is 480. Units are inches cubed. I need half of a circle here, and this circle, this entire side is labeled 4. So the half of the circle that's the radius is 2, but I don't have a full circle. I only have a half circle. Don't cancel this before you square it. Square first. That becomes 2 pi times 15. So it could be written as 30 pi centimeters squared. And 30 pi centimeters squared is 94.2. Cubed again. Okay, so our next step is to do a couple more things with those calculations of volume. We're going to find other things. They're going to give us the volume, and we need to find the base, things like that. We also have a comparison between similar shapes and finding the volume of more complicated shapes. So here we have a gold nugget. This is a standard size gold bar. They don't seem to be very big, but we want to find out how much it's going to weigh in grams. In order to do that, first thing we notice is they're asking in centimeters, but they gave me measurements in inches, so we're going to convert all of those. The conversion 1 inch equals 2.54 centimeters is an exact conversion, so we do that. Once we have all of those, we're going to take the volume, multiplying all 3 of those together because it's a rectangular prism. We now have our volume that is cubed, but now we go back and reread the question. And the question says, the density of gold is 19.3 grams per cubic centimeter. Find the mass of the gold bar to the nearest gram. So what we have to do is multiply the volume times grams per centimeter cubed. What happens is the centimeters cubed is going to cancel out, and I'm left with grams. And this is just a side note. They didn't ask me per pound, but you guys recognize pounds. 454 grams per pound. Here we have a cylinder that's made out of concrete. And we have the concrete density, so same type of thing. We're going to convert to centimeters. Then we take that to find the volume equation. The volume for a cylinder includes pi r squared. R squared occurs first, so we have a fairly large number here. And then multiply that by grams, so that centimeters cancels out, and we're left with 2,182,485 grams. Here we're looking for a missing number. We're looking for the height. We have the base. So we take the equation that we know works for rectangular volume. We plug in the things that were given, but in this case we need to recognize its volume is 72, not the height. That's the most common mistake on these, is we plug them all in over here. Once we have that set up, we're going to do the number crunching, and we get a height of 3 feet. Sometimes we have additional steps past that. So in this case, we only have the height, we don't have length and width. So in this case, we have something else that's missing, and we are going to be asked for what possible lengths and widths. So once we come up with what the base would be, we could figure out what width we wanted and calculate the length from there. So we start with the equation that has b instead of length and width. We plug things what we know. We solve that. So the base is 6 feet squared. The base is a rectangular, and so I'm going to pick whatever I want. I could have picked 2. I could have picked 1. I think 1.5 is nice deep drawers, so that's why I picked 1.5. Plug that in for the area of a rectangle equation, and that's going to give me 4 feet for the length. I could have plugged in a 1 and had a 6-foot length. I could have plugged in 2 and had a 3-foot length. Those are all reasonable picks. So we can have similar shapes that are 3-dimensional. So that means the scale factor is going to be worked on all 3 dimensions. When the scale factor is 2, we recognize that all of our sides have multiplied by 2. If we look at finding the volume by calculating it, we could pull these 2's out and multiply them separately, and so the scale of the larger shape is 8 times larger than this one, but the scale factor was 2. Well, 2 cubed, because all 3 dimensions got doubled, is how we get this is 8 times larger. So we end up with an equation for this. And this is probably the most common way that we set up the equation. We're going to have our scale factor cubed because we're dealing with volume. And then we can set that equal to a ratio of the volume of the larger and smaller cylinders. It doesn't matter how you set these up as long as you're consistent. If the large cylinder is on top, which it is for me, keep it there. So our scale factor here we find is 2/5. And then the volume is going to be 5 cubed, 2 cubed. So that's what we get here. And then the part that we know is the volume of the small one. That's why I put that on the bottom. Volume of the large one, that's our unknown right here. Cross multiply and divide this part here. So I just set this up, figured these out, then I'm not using this part anymore. Cross multiply and divide. So just pick A over B or B over C. Once you pick it, set up the equation that way. So I decided to pick A over B, and with A over B, I have a scale factor of 1/2. 1/2 has to be cubed. Notice I put it on both of them. So I end up with 1/8. The volume that I do know happens to be the smaller one, so I put it here. Cross multiply and divide. And I'm going to keep pi in the answer just because it's nice, clean, neat, more accurate. 360 pi centimeters cubed. Here's another set that we want to set up. Doesn't matter how you pick C over D, D over C. So if I decide C over D, I can see these guys being part of my ratio. C is 12, D is 3, and I'm going to simplify that because it makes my life easier. 4 over 1, those are what I'm going to cube. So I end up with 64 over 1. Then I take that cubed scale factor is prism D. Cross multiply and divide, and the volume of the small cylinder is 24 meters cubed. So you'll have a couple problems like this. You're setting up a proportion, and sometimes it might be that I'm missing the side length. All of them work. Just make sure that you're dealing with cube. So now we're going to take a look at a couple composite shapes. And in a composite shape, you may have two shapes that you add together, rectangular prism plus a half a cylinder. You may have two stacked rectangular prisms. Or you can have, like we show here, something is taken out. We have a hole. We actually have two holes in this case. So we're going to find the volume of the larger shape, because I can find the entire volume of this, because I have dimensions for those. Then I notice that the two holes that come in here are exactly the same dimensions, so I'm just going to say 2 times the volume of a small block. That's going to get me both of them. So then we set up our equations for each of those, the volume of the large block. We have our dimensions set up here, both the length and width, and the height. Then we have the two smaller ones, and we have those set up here. Now, over here we see these two dimensions. What's the height? Well, it goes all the way through, so it has to be this guy here. Then we number crunch each of those and find a volume of 0.4 feet cubed. On our last shape, it's another composite. So we need the volume of the rectangular prism and the volume of the square hole, and we're going to subtract that. Yes, there will be times that you're going to add two different shapes. In this case, it's sticking through the hole here. So, volume of a triangle. Tons of different ways of doing it. You guys have all three of these different equations. This is not do all three, this is pick one. So this top equation comes from equation 1/2 times A times B, two sides, times the sine of the angle in between it, which would be C. We did that a couple weeks ago. This equation here, how do we get 5 square root 3 so fast? This was, we used a 1, 2, square root of 3 triangle, 30, 60, 90. And in using that 1, 2, 3, square root of 3 triangle, we found this height. So this is base times height divided by 2. The last 6 here is the height of the shape to make the volume. And this last one here, this is 1/2 SAN. So we had to step to the side and find the apothem, but this is the apothem. Side length 10, 3 sides, this is the apothem, 1/2 SAM. Any of those work. You guys have more choices, more tools. So once we know which one we use for the triangle, all of these will find 260.1, and then I need to subtract the volume of the square hole, which has a length and a width that are equal and a height of 6. So this is 56, and we subtract that, 206.1 feet cubed. So those are the types of problems you're going to do today in the book. And if you have any questions, please make sure you shoot me an email. We will probably set up another Google Meet on Wednesday so that we can get together and ask questions about these. So if you struggle, please make sure you get started on these on Tuesday so that we can meet on Wednesday. Have a good day.